Many times, the basic vector search from a vector database fails to retrieve context that is fully aligned with user's intent and is also complete. There are a few well established techniques for improving vector search performance. Let us take a closer look at one of these methods called query expansion. Query expansion is a technique where the original query is expanded with related terms or concepts. Instead of relying on the exact words provided by the user, the system adds synonyms or contextually similar phrases. For example, a query like customer churn can be expanded to include terms such as subscription cancellation and attrition. Expanded query retrieves a broader and more relevant set of results from the vector database. The expanded terms can either be combined with the original query using OR clause such as customer churn or subscription cancellation or attrition, or each expanded term can be a separate search for which results can be merged before sending to the downstream large language model. There are a few ways to implement query expansion. The easiest solution for implementing query expansion is to maintain a keywords based dictionary. This can either be a custom dictionary of organizations' domain specific vocabulary, or it can be an external lexical resource such as WordNet. You can persist the dictionary as a structured JSON or YAML file, or you can even save it in a database. The runtime flow begins by splitting the user's query into individual tokens, followed by normalization techniques such as lowercasing of characters, removal of stop words, or extraction of core vocabulary words using stemming techniques. For each normalized token, a small set of related keywords are retrieved from the dictionary, limiting them to the top few to avoid exploring the query. For domain aware query expansion, you can further evolve the keywords based simple dictionary into an ontology. Ontology is structured domain knowledge with relationships such as hierarchies of parent and child nodes, related nodes, synonyms, or domain specific mappings. Ontology allows expanding the query with semantically related terms rather than surface level synonyms. For example, the query cheap laptop can be expanded using its synonyms with keyword space dictionary. But by using ontology, you can further expand it using parent or child nodes such as electronics, business laptop, gaming laptop, etc. Ontology can be saved as structured YAML or JSON file or in SQL or NoSQL database. For advanced use cases, ontology can be maintained in a graph database, which is a natural fit for business domain entity relationships. It is important to note that keyword based and ontology expansion techniques are classical information retrieval methods that were originally designed for keyword based search systems. They should be used if you are implementing hybrid search in your modern vector retrieval system. You could also use them if you're dealing with a large scale environment with strict latency and reliability requirements, or when you're dealing with a domain where terminology is highly specialized and complex, and your embeddings are not able to capture the domain perfectly and sufficiently. A more advanced use of keywords dictionaries and ontology is to assign weights to individual terms during query construction. These weights can influence how strongly each term contributes to the retrieval step. If each keyword or ontology term in the expanded query is searched independently, then the weights on these terms can directly affect the scoring and re ranking of the retrieved results. You can multiply the weight of the search term with the vector similarity score of the returned result to create the final score for that document. These weights can then be used to re rank the vector search results. And if terms are only used to build one expanded query, then the weights can be used to influence the query construction process itself. The weights ensure that we find everything important while also keeping the results precise. Log mining is another technique for query expansion, which leverages historical search logs for regularly updating the query expansion dictionary. The process starts with application logging users' session information, such as query text, the documents that were returned to the end user, the documents that were clicked by the end user, along with other session data. These logs are then cleaned by removing noise, such as any rare queries or incomplete sessions or any bot traffic. The cleaned logs are then mined to identify query relationships such as query to query co occurrence, where we find queries that frequently appear in the same user session. For example, if cheap laptop and budget laptop frequently appear together in same user session, then it indicates a correlation between the words budget and cheap. Iterative reformulation of a query by a user in a single session is also a strong indication that the words are related. For example, if a user started with the word laptop and then corrected it with cheap laptop and further by budget laptop under 1000, then this is an iterative reformulation of the query, which indicates that the terms are related. Another technique for finding query relationships is to measure query clicks. If different queries led to clicks on the same document by the end user, then they can all be considered related. Log mining is used to build the query expansion dictionary of related query terms along with relevant score with each term, which can be based on click through rate or co occurrence strength, etc. Saving the logs in a vector database is a scalable method of using historical user logs for query expansion. Log information such as past queries, clicked documents, or even full search sessions can be embedded using a sentence embedding model and then stored and indexed in the vector database. Remember, this index is different than the retrieval augmented generation index that we create by chunking the organizational data for retrieval. During retrieval, the user's query is first embedded using the same sentence embedding model, and then a semantic search is performed to retrieve semantically similar past queries. A combination of approaches can also be used in a hybrid solution. Ontology can first generate precise rule based expansions using domain specific knowledge. Vector database can then complement it by expanding the query using historical query logs that are not explicitly coded in the ontology. Systems that have important domain relationships, such as healthcare, legal, e commerce, can benefit from this hybrid approach. The last solution that I want to discuss is the most dynamic of all the solutions we have discussed so far. You do not need to maintain any dictionaries or vector index, but rather use a large language model to rewrite the query. Large language models are one of the most popular and effective methods for query expansion, as they can understand the intent and don't just rely on the words. They can also inform missing context and are great for complex or vague queries. They are, however, expensive at scale and can also add latency. They can also hallucinate with irrelevant expansion, which is not grounded in the real user historical data. To summarize the various solutions that we have discussed for query expansion, weighted keywords and ontology based dictionaries are easiest to build, and they can be the first place to start. As a next step, you can consider building log mining system with an optional vector index. Large language model based query expansion is a very effective technique, but you must evaluate this approach for latency and cost impact on your application.